Hello, my name is Misha, and today I'm going to present perceptual error optimization for Monte Carlo animation rendering. Monte Carlo rendering produces visually displeasing noise in both space and time. We could perceptually improve it in spatial domain by using blue noise distribution. However, despite good spatial distribution, even the state-of-the-art blue noise methods, as shown here, produce temporally unpleasant result. And today, we are going to present our method, which can achieve perceptually more pleasing error in temporal domain as well. But first, a bit about background and previous work. So what is blue noise? As an example, let's take digital halftoning, which approximates grayscale images with only black and white pixels. Now, instead of constant threshold, we can also use random threshold, which will give us more detailed but also noisier signal. If we would now rearrange the values in the random threshold such that they are as different to each other as possible, we are going to get significantly more pleasing image. And this is because the power spectrum of this threshold does not contain low frequencies to which our visual system is most sensitive to. This is known as blue noise. And first way to achieve it in Monte Carlo rendering is to optimize samples to have blue noise distribution, and hopefully our rendered image will have this noise distribution as well. I say hopefully because in case of high dimensionality and complicated integrals, this does not translate as nice blue noise. So far, the previous work was only focused on spatial optimization. The only exception is recent work from Wolf et al., which was the first attempt at extending blue noise to a temporal domain. However, this is not the only way to achieve blue noise. A posteriori optimization first renders the image and then it tries to optimize the samples. Using these samples, we can re-render the image and get almost perfect blue noise distribution in all scenarios. However, this is not, all the previous work is not very practical and spatial only. Let's now dive deep into a spatial temporal perceptual framework that we are proposing. So the cornerstone of human visual system is known as contrast sensitivity function, which explains how humans are sensitive to different spatial frequencies in this case. And previous work has been able to nicely approximate this as a Gaussian. Here's a little illustration. On the left, we see raw white noise and optimized images, and on the right, we see how this is actually how we are going to perceive it, assuming this kernel. However, when we talk about spatial temporal domain, contrast sensitivity function is much more complicated as it's both function of spatial and temporal frequencies. Luckily, we can approximate it as a pyramid in log space. Base of this pyramid is representing all the frequencies we can see as humans. By the way, this is known as window visibility. Thus, our key idea is to move as much Monte Carlo error outside of this region as possible. But how do we know how we can approximate this window visibility? Well, we already have a spatial kernel, and if we can find a temporal kernel, we can convolve the two and get our approximation. And it turns out that our temporal vision consists of two channels. Sustained channel, which encodes slow changes, and transient channel, which encodes fast changes. And adding the two up, and we get our kernel. And mathematically, our optimization tries to minimize the rendered error convolved with our approximation of window visibility, i.e. convolution of temporal and spatial kernel. And once we evaluate it a posteriori, we get very nice results. We are, of course, basing here on top of the Vassal and Chizhov's state-of-the-art method, but as it needs a reference to compute the images, we also need references up front. So let's make our method practical by making a priori sample optimizer using our theory. And we are going to base our optimization on slice optimal transport, presented first in these two previous works. And for sake of simplicity, we are just going to, for now, consider 2D spatial temporal space. We're going to start from white noise and try to reduce Wasserstein distances using stochastic gradient descent. Out of bajillions of spatial and temporal kernels, we are going to only select one spatial and one temporal kernel, then randomly threshold them to select samples, and then these samples are going to be projected to a random 1D slice. And then we are going to use optimal transport to basically compute 1D Wasserstein gradient. And this is going to be repeated until convergence. Now let's talk a bit about results. So here we can see our perceptual results, and we can see that we are improving over the previous state of the art as much as it improves, not over other blue noise works, but white noise. And to make this more easy for you to see, we have temporally convolved the video. But let's now think why this is significantly better. And for that, we need a single frame comparison. So it turns out that in spatially only single comparison is actually our blue noise properties are slightly worse than previous state of the art, i.e. Wolfe et al. And that means that all the improvements that we are doing are coming from temporal domain. And this actually makes a lot of sense because Wolfe et al. Disjointly optimize for temporal and spatial domain, which does not coincide with our perceptual kernel, meaning that their residual error is going to be significantly higher than ours. But that is not all. We are also including in our optimization explicit filtering, in this case temporal anti-aliasing, which is very common in practice. And we are going to simply extend our optimization, and as we can see from our results, we are getting same improvements as we have seen with perception. But this is not all two results we have achieved. On the bunch of scenes, on the different temporal kernel configurations and combinations, on different spatial kernel optimizations and different sample counts, we see that we are consistently better than the previous state of the art. But this work is also about pointing at limitations in future work. So let's have a bit about it. So first is the fact that in perception, we assume that there has been some accumulation of signal happening in our retina. And this is not the case when we have rapid motions or if there has been abrupt change in the signal or something like that. And this means that at the very first frame, there is not going to be much of the blue noise as compared to static blue noise or spatial blue noise. However, as time progresses and this accumulates in our retina, we can see that we are getting significantly nicer blue noise characteristics in, for example, frame 20 compared to spatial only blue noise. Other issue is the fact that our a priori optimization is significantly worse than our a posteriori optimizations. In this case, actually 5 times almost. And it's very simple to understand why, actually. Blue noise is effectively a compromise between white noise and regular pattern. And it's already very difficult in 2D to get this compromise. However, once you extend it to 3 dimensions, it's even harder to converge to correct result. And last but not least, well, people are not anymore interested into just having a nice noise. They are probably going to use the noiser. So the question that's going to be on everybody's mind is blue noise helping us having a better denoised image? And it's not a straight-cut answer, because in certain cases, we are not going to get low frequency error, which is going to make it much nicer, but in some other cases, it's going to be over-blurred, meaning that it's going to have larger error and being worse than white noise image that has been denoised. But overall, it makes a lot of sense to do this, and we are going to build intuition by just using a static kernel. If we would try to use it over blue noise to just reconstruct it, we're going to get almost perfect reconstruction of constant gray image, which is not going to happen with white noise image. And of course, this has been also confirmed with power spectrum analysis. However, it should be noted that once we use blue noise and denoising combination, our stuff does not becomes just perceptually better, but also numerically. And just to conclude, we have basically presented our spatiotemporal framework, which we have also evaluated using a posteriori approach. We have then computed our spatiotemporal tiles using our a priori optimization, and then basically get wonderful and state-of-the-art results in an animation rendering using these temporal tiles. Thank you so much for your attention. Bye-bye.